All right. Before we actually talk about Envoy, we want to talk a little bit about what the Edge Cloud is about. What are the architectural constraints the current proxy model has, and how is Edge solving that? And how is Envoy especially fitting in that Edge architecture? So that seems like more of an interesting way of looking at Envoy because it has some cool features that fits right at the Edge architecture. So we'll talk about the current set of architectural impacts of using a data center-based point of presence proxies, and see how that translates if you were to take that proxy and then move it out to the edge, what happens? And so does that yield some desirable properties, or does that have any challenges that we may want to address? And we would like to see how or what the specific edge constraints or consideration that we should have in order to move from data center to edge. And then we'll talk a little bit more in detail about how Envoy solves it, especially on the routing dynamics, especially on the extensibility and programmability of Envoy, because that's the key on the edge. We'll probably reserve the question and answer to the later sessions. So if you look at this is a large-scale, geographically distributed L4, L7 proxy world that's deployed today. Without having to name any specific companies, you would see these points of presence proxies that are deployed in various cities, typically, like San Francisco, New York, Atlanta, Dallas, for that matter. And they are actually serving a bunch of local branch offices that is connected to the nearest point of presence. So the one on the left is the branch office. The one on the right is actually the internet services that we wanted to serve. The blue color is not as clear, is the cloud that's serving all these enforcement points. So this is vastly different from the hub and spoke model that data center world or the telco world is used to. This is the current architecture, but we're going to talk about the edge architecture, which is even more distributed. So if you see here, you see a bunch of control plane clusters that's widely distributed. You have points of presence or the proxies that are distributed in different cities, and you have logging and other clusters that are supporting that infrastructure in different parts distributed worldwide. The reason I put up this architecture is there's some set of inherent challenges architecturally that would be only solved with going to an edge, and so we'll look at those things. Mind you, all this is sitting in a wide area network, so you typically have to go from a branch office to a cloud through an MPLS based overlay network. So that's also something that would add up the expense and cost. So what is the architectural challenges that allows that kind of constrains the data center world that we talked about? For the very first thing, it's going to be resulting in a global DNS outage much more often, because we are primarily relying on the DNS and the NS delegation model to be able to set up routes. And if you see this, these routes are nothing but DNS anycasts. So a point of presence is something like a virtual IP, if you can think of virtual IPs. The virtual IPs are different in different parts of the region. The DNS anycast would set up a client to connect to the nearest point of presence geographically. So that's an anycast model. So this leads to inconsistency in the config because you're now relying on the protocol semantics. Things like TTL caching would actually add up those cache coherency. It is also difficult for the configuration changes to be propagated across regions, because the decentralized nature is going to actually make it more of a pull model as opposed to a push model. So you would have to actually have the proxies pull the configuration from the nearest control plane, for instance. And obviously it leads to several scaling architecture. You need to have more workloads, instances, and whatnot. It's also quite a bit difficult to add protocol awareness. It's a major bottleneck to incorporate because you would expect the point of presence to typically run same or similar version. You wouldn't expect to run two different versions of proxy enforcement or proxies in different regions. And so the Canary support is obviously limited. It also adds to elasticity in terms of scaling out more instances. If you want to add more VIPs, it's going to be much more than just workload. You would have to buy IPs, you'd have to increase your LB instance capability and whatnot. So it's quite a bit of a static model still. It's distributed, but still static. What's interesting is these edge migration is actually solving some of those problems, and this is how it is doing it. We are breaking up the larger clouds into much smaller pieces, as the COD world suggests, primarily because we want to expedite the localized processing. We want to expedite the latency that's coming in from the client all the way to the services. The explosion of deployment types, for instance, Docker-like microservices-like deployment, is actually helping in exploring of these edge services, because now you actually want to have the localized container world talk to a localized control plane. In fact, COD model actually advocates these two philosophies: economics of the data center with the agility of cloud. So you could achieve only through certain architectural changes. And so we're going to look at what those are. So these are some of the desirable properties of an edge proxy. If you were to actually take the current point of presence and then move it out to the edge, this is what I would typically want to have. You would want to have very flexible, lightweight, platform agnostic deployment, for instance. And that is relatively eventually consistent much more in a shorter time as opposed to a wide area network. You would also have to make sure that the traffic is localized and distributed just locally and not have to traverse the wide area network. Of course, the primary thing is to be config driven, because the moment you actually move your proxy to the local world, it would want to be much more elastic. You're dealing with a lot of these edge clouds, which means a lot of these proxies would have to be consistent in a way that's driven by configuration. So you want to have a config-driven API, and that talks about route programmability and extensibility. So that's an obvious choice of it's a requirement. MTLS is a big requirement right out of deployment, because you cannot do things like man in the middle anymore. All the data is actually moved to the edge cloud, so you can't send it out anymore out of your cloud. So all this is actually pushing the requirement for edge in a much more seamless way. But the thing to keep in mind is we're not looking for high performance ASIC-like performance here. There's going to be inherent limitations in what can be supported because it's all in software. There's going to be less features. Keep your configuration simple. So just to give a unforeseen side effects, but we'll kind of review it at the end when we talk about Envoy. So now we'll go a little bit into Envoy and to see what it supports and how it actually helps in the edge architecture. It's a very high performance, lightweight, small footprint, open source proxy. Has core L3, L4 level support, and all the way up to L7 custom filters. You would be able to do first class HTTP 1 and 2. There's a lot to do on protocol extensibility and programmability that we'll talk about. Finally, Envoy also supports extensive observability, which is a very important aspect, because as the number of deployments explode, you want to have a very different way and very unique way of collecting statistics and traces across all the edge clouds. Just to be familiar with some of the terminologies. So an upstream is something that a host receives connection from Envoy. Downstream is something that Envoy connects to. Listener is a connection metadata for the local network, the set of network protocol and the ports that's connected locally. And cluster is one of the most important components, which is, you can think of it's like a logically similar upstream hosts that is kind of load balanced at the server side, but we'll talk about it as a cluster. So this is one example of how Envoy supports dynamic configuration. So this is how a control plane drives Envoy by sending a bunch of control plane data. So the config model in here is the specific clusters, routes, endpoints, and the listeners. So the specific control plane that is of interest here is Istio Pilot that supports this data model. The important aspect in this diagram is Envoy supports these blocks as a unique programmable data structure in memory. So whenever a control plane changes listeners, for example, or clusters, for example, you would have Envoy take up that particular data structure and rewire it in such a way that no restart is required. So that is the dynamic mechanism that is of interest to us, and that's of very interest in the cloud, in the edge architecture as well. You can also notice that between the listeners and clusters, there's a bunch of L4 and L7 filters that we will talk about. This is another example of how Envoy drives the data plane using a control plane data model such as Istio. In this case, the Envoy is sitting as a sidecar next to the app, and it's actually pulling information from the control plane to form the data model of interest. So you could also do push using gRPC streaming, and that is much more faster. So by that, you mean the pilot would actually keep the connection open to the Envoy sidecar services, and you would actually have these endpoints connect and make changes on the fly. However, there is no ordering guarantees except when you use a slightly different model called the aggregated discovery service, where you would actually allow a single stream to connect and obtain all this different resource from the control plane. So you can also have these faster updates using these the pull configuration, but usually the push is much more of consistent and much more of a faster way of doing things. No Envoy restarts here, and it maintains the dynamic state information on the fly. So the aspect of this is when the RDS, the route discovery service, finds the route, Envoy is able to, at that point, take the packet and do the parsing and mutate the HTTP request. And the important thing is it makes this on the fly. So even if there are route changes, the data structure takes care of actually building the structures in such a way that the filters are automatically applied to the packet that's coming in. So for instance, this is one example of how an upstream connection is initiated. So you would parse the HTTP request, and you would apply the filter and try to match the upstream connection, and then set up the connection pool and forward the request. The reason I mentioned that here is because you actually have a lot more ability to apply filters of interest to listen and to apply the type of filters that you would want before you actually send the connection out. So Envoy supports that very much. Router filters is a way to support extensibility. You have network and HTTP level filters that can be programmed, and you can actually, for instance, have HTTP path matching and prefix matching kind of filters that are, in fact, the community encourages several people to do the L4 and L7 filters, to come forward and do the filters to be able to make it much more extensible. So that's the whole point here. So you can even add custom filters on top of HTTP. So here's an example of such a custom filter. Basically, we are taking a virtual host with a star domain, and we are rewriting the host to google.com. This is actually a HTTPS connection, so you would actually be able to change the 443. But so this is how a typical YAML configuration looks like for Envoy. So I want to talk a little bit about the extensibility. Envoy at its core is highly flexible and it's extensible, right? So the first thing here to look for is listener filters. So this is typically a broad level view of the connection model. So when a worker comes in with a particular packet, you would actually establish a connection. But even before the connection is established, you would talk about the listener filter. So listener filters are nothing but connections that are established before the metadata of the connection that you want to establish, before you actually establish the connection. And by doing that, you can filter quite a bit of ingress connections itself. For instance, you can actually write listener filter with destination port, destination protocols, including SNI for that matter. And only if it matches all of those would Envoy allow you to make a connection for that matter. And then comes the TCP filter manager, where you actually have support for read and write filters. So that's considered L4 filters, which would have to satisfy before you actually go to the L7 filters. So the L7 filters are fairly generic. You can actually specify HTTP level host headers and much more in deeper. So when all these filters actually go through successfully, that's when the Envoy establishes a connection pool to take that forward to make the appropriate policy enforcement. So this is a classic example of how you can make that extensible. So each of these custom filter in each of these parts of the stack is highly extensible. And that's a very critical feature of edge routing. To talk about programmability, there's some things you can do in the before Envoy actually routes out. You could do label-based routing, for instance. You could also do content-based routing. There's priority-based routing that allows route-level priorities to be implemented based on connection pool and circuit breaker information. For example, this is a label-based routing mechanism that allows traffic splitting. So service A talks to service B. If you have two versions of service B, you can probably have 99% sent to service B. That is with version 1.5, and just 1% as version 2 alpha. So you could do these kind of things with labels. The labels are typically tags that you actually mention in the custom filters. You can also do content-based routing. For instance, you can actually send certain parts of the traffic to matching user agents, as in this case. These kind of things allow you to do Canary support fairly easily, and that's it's a very desired requirement for edge computing. So, as in protocol supported, we have Envoy supports HTTP 1 and 2, WebSockets and gRPC. UDP is in progress, and MySQL is also in progress. There's much more filters and protocols that can be added in future, which makes it an ideal edge computing proxy. So there's one change in the expectation that we would have to make if we were to use Envoy, and that is to do with load balancing. If you use any of these, the Datacenter Proxy Well load balancing, you would have seen that they are centrally managed. You would probably procure a few virtual IPs and then have multiple of these workloads behind the virtual IP and configure those load balancer to make appropriate decisions to route to specific instances or workloads. That does not hold here anymore, because the scaling of edge would not allow us to do that. Long-term connectivity like gRPC would end up making a sticky connection to only one or certain virtual IP instances, which means we have to think about client-side load balancing a bit. And that is actually becoming popular, and Envoy supports that as a first-class service. By that, what I mean is the the client that's originating the request is able to decide which particular destination that it can route to. By doing that, it actually becomes a true distributed load balancing on the client side. So there are other features on the edge that are of importance. I think Canary support is a very important one. To be able to do traffic splitting, to be able to try out different services before you actually deploy them. Application security and TLS, you can actually make Envoy present certain certificates between services that allows you to authenticate the services themselves. And that is completely different from the service-to-service authentication. So it basically supports RBAC out of deployment. And we would talk more about that in the next talk. You can have things like rate limiting by just having custom filters. Access logging is another important aspect of Connection Manager. So in summary, it's an elegant way of doing proxying at the edge. And you could see that the configuration model allows you to extend it. You can actually do a push-based configuration, which is very interesting and very fast paced. You cannot do that on a wide area network point of presence. And everything is localized, which is what Edge would want us to do. An important aspect is the mesh sidecar model that actually takes away most of the control plane overhead in providing the distributed policy enforcement. So for example, the application health checking, DNS updates, TLS termination, all these would have to be done in the control plane in a distributed wide area network point of presence. It's all taken care by Envoy for you here. So there's tons of materials on Envoy, but in summary, Envoy is a very elegant implementation of what an edge proxy would look like architecturally. And that's all I had. Thank you.
Questions? Yep.
Thank you. Thank you. Basically, I want to understand this Envoy is a proxy. So if instead of cloud, we use it inside enterprise at an edge proxy, where, so does it support HTTPS connection proxy? Basically, the enterprise users are trying to make HTTPS connections outside. So this proxy is the HTTPS connection, and it makes the connection to actual server on the behalf of user.
Right. Okay. So the question is if Envoy would be able to support a forward proxy model by terminating as TLS. So it does not support forward proxy model yet. You're typically looking for a man-in-the-middle kind of a proxy, and that does not support. It is in progress, I believe. But you can actually allow you to do a reverse proxy with MTLS termination and also between services. So you can actually get rid of the man-in-the-middle model altogether, and you can have the services deployed on your private cloud and some services on the web and have them talk TLS and Envoy take care of it. And that's how you would solve it. You would not go the man-in-the-middle anymore. But
what sort of ways do you go about monitoring Envoy deployment?
Envoy generates a lot of statistics and trace information. It is compatible with Zipkin. If you're aware of Zipkin trace management, all these are open source. For every transaction that, for every connection pool that establishes, Envoy generates statistics that are sent to another control plane daemon if you wish. And you can actually have between connections the request that's going in, the responses that are coming in, and all kind of statistics configured in a filter, in a different filter, that it can be exported to the control plane. And you can do much more with that.
Okay, thank you.
Is that
Other questions? I have one. If you go back to your very first architecture slide.
Sure.
I just want to make sure I understand the connection from today to tomorrow.
Right.
So it's okay. You can name the blue sphere if you wanted to. So you're basically talking about the proxies that are there today, and you're just imagining those going out further to the edge.
That's right.
And as a consequence, they are at a central office choke point.
Right.
And so therefore you're not depending on the DNS as your routing mechanism. Was that a key part of it?
So
To find the best proxy, so it's automatic.
that's right. The DNS anycast is to find the best proxy that I initiate, the geographically closest one would have to be a LAN base like this. And if you break up the cloud into like thousands of edge, you cannot use the distributed DNS model anymore, because obviously you have to have DNS to make sure they are fault tolerant. You have to have multiple of these DNS serving the same set of services. And you also are dependent on the cache and the TTL, so it wouldn't scale.
Okay, so it is Envoy routing at the edge in lieu of DNS-based redirection.
That's right.
Okay.
That is exactly right. Yep.
All right. Other questions? Okay, thank you.
Thank you.